So we found the Hamiltonian of the system here. Let's get now the Jacobi equations in action angle coordinates, where this theta here is not the polar coordinate, it's a generalized angle. Don't confuse them. Right now, let's use only the first one. And as you see, there is a complete symmetry with the actions. So all of these frequencies have the same expression. Apply that for the radial coordinate, apply that for the polar or the azimuthal, the result is the same. You have that all the frequencies are equal to gm squared over jr plus j theta plus j phi cubed. So it seems that these coordinates are not yet coordinates that help us solve the problem in a simpler way. We can simplify the problem further. That's where the Delaunay variables come in. If the action always appears in sum, we can actually turn that into another action of the problem. Let's define another set of angle action variables where jr plus j theta plus j phi is an action. That means that we're defining a new set of three actions, let's call it JA, JB, and JC, where this new action jr plus j theta plus j phi is one of these. And we don't know yet what the other ones are. So we don't know yet what these new actions JA, JB, and JC are, but we have a few choices for them. We know that one of them is the sum of the actions. And we know also that j theta plus j phi is the angular momentum. And the angular momentum is constant, so let's use that also as an action. So these are our choices here. One of these actions here is L, and the other one is JR plus L. So let's see how we can do this. We had actions before where one of the actions, J theta, was the angular momentum minus the angular momentum in Z, and J theta and J phi was the angular momentum in Z. We can keep similar actions. Let's keep JA equal to LZ, but let's define it now so that JB is equal to the angular momentum. And the last one by definition then was the one that was the combination of the three of them. It's JR plus J theta plus J phi is the angular momentum. So we have our new set of actions. We have J phi is equal to LZ, which is equal to JA. We have that J theta is equal to L, which is JB, minus LZ, which is JA. And JR is equal to JC minus L, which is JB. Okay, so these are our new actions. JA is the vertical component of the angular momentum, JB is the angular momentum, and JC is what appears in the Hamiltonian. So we have now a Hamiltonian that is very simple, depending on only one of the actions, JC. That makes it very easy to solve the equations of motion. Let's apply now the Hamiltonian equations for the angle action variables. Theta dot, which is a frequency, is equal to the derivative of the Hamiltonian with respect to the action. So what is it that we have? We have that the Hamiltonian depends only on JC. That means that the frequency for A is equal to 0 and the frequency for B is equal to 0. So whatever is the angle A and whatever is the angle B, they are constants. As we're going to see, these angles are the argument of pericenter and the longitude of the descending node. These angles are constant. That means that the orbit doesn't change orientation. The only one here that changes, the only angle here that changes is the C. So the frequency C is the derivative of the Hamiltonian with respect to J, which will give you gm squared over JC cubed. And if JC is an integral of motion, then that means that this angle C increases linearly in time. As you're going to see, this theta C is the mean anomaly. So there you go. You will have then two angles that are integrals of motion. We have three actions that are integrals of motion and one variable that is periodic. This is the solution of the Kepler problem, which we found earlier through Newton's laws, done now via the Hamiltonian formalism. We have five integrals, three actions and two angles, and one angle that is varying periodically in time.